All right, so this video is going to focus on how to solve distance, rate, time problems using rational equations. And you should remember from earlier science classes that the relationship between distance, rate, and time is distance equals rate times time. But a lot of the times that we're going to be using these, we're going to want to know that rate is distance divided by time, or time is distance divided by rate. And you'll see that in just a moment. So we have an example here where we have a lady named Sandra who is canoeing, and she can canoe in still water at 6 miles per hour. It takes her 3 hours of travel to travel 10 miles a round trip in the Chattahoochee, and assuming a constant rate of speed, determine the rate of the current of Chattahoochee. So that constant rate of speed is the constant current, and she's also constantly rowing at 6 miles per hour in still water. So you know how we did the chart with the weighted averages stuff? We're going to do sort of the similar thing here with this problem, but this time the charts themselves are going to be distance. The columns are going to be distance, rate, and time, and the rowing is going to be upstream, which is against the current, downstream, which is with the current, and then total. All right, so what we've got here is we know that she can row 6 miles per hour in still water. That would be a rate. However, she's going to be rowing in a current. So if you think about the way that that currents would affect how you row, if you're rowing with a current, it would be like you're rowing 6 miles an hour on your own, but the current adds whatever its speed is to your speed. And if you're rowing against a current, it would subtract away from your speed, so you'd be going relatively slower. So when we're looking at the rates here, we're going to say the rate upstream is going to be, let me lock this because it's trying to do a super zoom here. The rate would be 6. Get my pen back. 6 minus, let's say her rate is W. That would be upstream because it's her rowing minus what the current is pushing against her. You couldn't do it the other way because you want the bigger thing first. And if the current is bigger than her rowing speed, she's never going to make it upstream anyway. So you always want to put the rowing speed first when you're doing the upstream thing. Downstream, however, the current's going to be adding to her flow. So I'm going to do 6 plus W here. Now, the problem says that she's taking 3 hours to travel 10 miles round trip. Those are total times, right? So this is 3 hours, and this is 10 miles. Now, here's the thing. When you think about time, rowing upstream and downstream, those would probably be different, right? Because you should be able to go a lot faster rowing downstream than going upstream. So it's going to take longer to go upstream than downstream. Those are going to be 2 different times. But the distances, if she went round trip and it was a 10-mile round trip, she ended up back in the same place she started. So at some point she had to turn around, and it would have to have been the same distance going up as coming back. So when we look at the distances, round trip, those would both be 5 miles, but the times would be something different. We do know, however, that those times can be calculated because we have a distance and a rate for each of those legs. So if you look back up here at the top, we want time. So time is distance divided by rate. So I'm going to say distance, which is 5 over this rate, 6 minus W, and then the distance 5 over this rate, which is 6 plus W. Now, those 2 times, when you add those together, just like in the weighted averages thing, should equal the thing at the bottom. We saw that in the distance column as well. So now I have an equation that I can set up and solve. And I'm going to solve this by doing the way that I've done it before. We're going to build a pool. 6 minus W is already fully factored. I could pull out a -1 if I wanted to, or I can leave it the way it is. 6 plus W is already fully factored. And then the denominator of the 3 is 1, so I don't really have to throw anything in the pool. I'm going to multiply both sides of that by the LCD. like that. Going to cancel appropriately. I'm going to multiply everything out that's left. Let's see, that'd be 108 minus 3w squared. So now I'm going to combine like terms. I'm going to solve by getting the w stuff by itself, dividing by the coefficient, and then taking the square root of both sides. Now technically, the answer could be plus or minus 4 here, but since we're talking about a current, it's just going to be 4. Negative current doesn't really make sense, right? So it's going to be 4 miles per hour. And that's the current of the water. All right, so pause the video and try the problem at the bottom. First, I'm going to draw my chart. Notice that I'm using against and with rather than upstream and downstream, so I'm against the wind or with the wind. Now I'm going to fill in what I've been given in the problem. Since it's a round trip, I'm going to split the distance in half for against and with. I'm going to use the speed of the wind with the speed of the plane to calculate the rate against and with, always putting the rate of the plane first. I'm going to get the fractions now that represent time, which are going to be distance divided by rate. I'm going to add those times together to get the total time. I'm going to get the pool, the LCD, and multiply the whole thing by the LCD on both sides. I'm going to cancel appropriately. I'm going to multiply things out. I'm going to combine like terms. Notice this one's quadratic, so I'm going to solve it with a quadratic formula. And we'll disregard the negative answer because it doesn't make sense, and then put units on our answer. So 339.46 miles per hour.